So that we don't have that much time left together, and you're like, to heck with that. To heck with never having you for class, Dr. Mike. Wait, we're canceling class Tuesday. See how it is. All right, let's go through some quick updates. So the attendance grades are up to date. I made a really big post pretty much between now and the end because we don't have that many lectures left, especially given the fact that I'm canceling class on Tuesday. So everybody pay attention because I want everybody to be clear. So, homeworks 8.1 and 8.2 are being graded. I think I still have a couple emails to respond to. I'm still digging myself out of that. So if you sent me something, I promise I didn't forget. I just haven't gotten to it yet. Homework 8.3. Because I was a little delayed in getting it posted, what I decided to do was combine that. The two problems that are on homework 8.3 are incredibly short. They're not long. If the last two homework assignments have been any illumination of that, I think you'll get what I'm talking about. So today, and to be honest, this topic is pretty easy and it's pretty short. Today we're going to talk about thin-walled pressure vessels. It is a class of a combined loading problem that has applications in various fields, and the math is actually really easy, so it's a pretty classical problem at this point in the course. Now, homework 8.3 is going to contain one combined loading problem involving a beam and another thin-walled pressure vessel problem. That's due Friday. What we're going to do on Thursday is we're going to discuss our final topic in the semester, which is elastic buckling, buckling of columns. What we've been doing up until now is we've been treating tension and compression in the exact same fashion. And the problem is, it doesn't always work, especially when you have elements that are inherently slender. You will find that they are much weaker under compression due to their tendency to buckle. And so our final topic in the semester will be to discuss what buckling means, what are the solutions available to us to assess buckling, and then we'll do some example problems on that. What's topic is I'm probably going to take all of lecture Thursday covering it. And there may be a few minutes left over, like one example or something. What I've decided to do is I don't think that's enough for us to get up at 8 o'clock in the morning. And at the same time, I don't want to cram, like I could probably find another topic to cover, but I don't want to cram that into the end. I'm all about covering topics and covering them well. And so what I've decided is we're going to do elastic buckling on Thursday, and then we're just going to go ahead and cancel class the following Tuesday. The final homework assignment is going to be due Thursday, 8 a.m. when we come back. So on Thursday, April 21st, lecture 28. On April 21st, we're going to come into our exam review. You turn in this assignment. I give you the solution. We go through final review. We have our final, and we are done with Engineering 216. So everybody okay on the logistics? Okay, now, a couple of other things. So number one, I made a really detailed post about logistics and specifically regarding the final. I had a typo on my syllabus because my syllabus was still using the schedule from when I taught this class back in fall of 2018. So the final exam is going to be during the normal university exam time slot. It's Thursday, April 28th in the morning, same like the same time slot that's been assigned. So my apologies for the typo there. One thing I did want to mention are these two boxes here. So first off, the at-home game spreadsheet. The reason I didn't want folks to edit that on Teams is because when you edit it on Teams, everybody can see your edits, right? So the moment after I posted it, somebody edited it on Teams. And so I deleted the data and I said, okay, don't edit it on Teams. And then after I hit that reply, somebody edited it on Teams. So I just deleted it and I just emailed it to everybody because I didn't want, I wanted to try and maintain confidentiality as much as I could. So everybody has that via email. You can play the at-home game to your heart's content and figure out what you need to get on the final and whatnot. Now, bonus homework. I say here that the bonus homework is to be posted once the survey opens. for those of you that haven't had me for class before, which is, I think, the minority in here. So what I do is I have a bonus homework at the end of the semester where if you fill out the course eval, and again, you could say I'm the worst professor ever, but as long as you do it and upload proof that you've done it, I will give you 10 bonus homework points on top of your homework average. So 3 points. And again, I'm just interested that you do take the feedback pretty seriously. There is one thing though, I actually am genuinely interested in to hear your feedback. I am hoping, as are we all, that at least here, that the major waves of the pandemic are hopefully behind us, right? It's been 2 years now since the pandemic first hit us, and I think that we had to learn a new way of doing things. We had to learn a new way of doing business. And so we adopted tools like Teams and OneNote via, in your Teams channel so that everything we do on the board you can access at home. But the pandemic is hopefully behind us, and I'm curious, moving forward, are there any strategies that we've employed that you think we should continue? Any strategies you think we should stop? That's honestly, genuinely what I'm interested in. So if you have any suggestions, I really would take them to heart. I'm curious about that. But yeah, ultimately though, that evaluation's about me and the class more than it is about just your general experience here. But again, if you have any suggestions, please, I'd be well open to them. Any questions? All right. So we're going to come Thursday, talk about buckling, canceling class the following Tuesday, and everybody knows the homework deadlines. Homework 8.3 is due Friday at 5 p.m. Homework 9 is due the following Thursday at 8 a.m. Sound good? Okay. I do want to make sure. Okay, so let's get into it. I want to make sure that everything. We're only going to really need to use part of it for this problem as we get into it. But the idea is that Mohr's circle will essentially perform all of these stress transformation analyses for us in one fell swoop and tell us worst case scenarios for our applied stress state in a very manageable set of plug and chug expressions and a very simple graphical plot. Okay, so the idea is that given a stress state, so given sigma x, sigma y, and some shear stress, what I can do is, theoretically, what I can do is I can take that stress state, rotate my coordinate system, and get a new stress state. That's well and good, but as an engineer, I'm interested in worst case orientations, worst case stress states, because I want to be able to design this system. So Mohr's circle will tell us the new stress state under some orientation, but ultimately, because it's a circular plot, we can take the extreme values on the x-axis, or the normal stress axis, if you will, and those are our worst case normal stresses, and then the largest value in the y direction, which is essentially the radius of our circle, is the worst case shear stress. So given a stress state, I can determine what is that worst case orientation and worst case normal and shear stresses very expeditiously. All right. Any questions on that? Now, there is something though that I think is worth mentioning. If you go back to the problem we did, we looked at the beam, and then we had that circular element that had the axial load, the torsion, the moment, and all that. We were able to remember how I said that the last lecture was sort of this culminative set of examples which combined everything we did the entire semester, and we ultimately arrived at taking what we did on day one and combining it all the way up through Mohr's circle. But there's something that was kind of interesting. Did you notice how the stress states that we derived for those problems didn't have any sigma y's? We had a sigma x, we had a shear stress, but sigma y was 0 for both of them. And I'm curious, are there ever any real-world examples where we get a sigma x and a sigma y? Well, there's oodles of them. I mean, for example, I can think about civil engineering land where we've got stresses in a soil media subjected to foundation, we've got hydrostatic stresses, et cetera. And so Can you get stresses in this direction, this direction? Oh, you bet. Any object that I would argue has maybe irregular geometry in engineering systems has a very high propensity for just stresses all over the place. But there is a very common example of situation that we deal with in 216, which is a thin-walled pressure vessel, which has applications, surprisingly, in disciplines beyond mechanical engineering. But if you're wondering, well, how does that pertain to sigma X and sigma Y? Well, the easiest example I could think of is imagine I had a balloon, right? If I take that balloon and I inflate it, right, it is stretching, right? And it's basically sort of stretching radially, right? It's stretching this way and this way, right? So there is going to be a sigma X and a sigma Y, just as there is with a pressure vessel. Okay, so let's talk a little bit about pressure vessels. So what we're talking about, at least for the applications in this class, are essentially any cylindrical or hollow, any cylindrical tank or cylindrical system that is subjected to an internal pressure. Okay, and so for our analysis, now this is a point that's worth mentioning. For our analysis, what we're doing is we're assuming that the wall of the pressure vessel is small in comparison to the diameter. And the reason, so that's one of the assumptions that we're going to make. I guess maybe one of the questions is, what does that mean? Or like, what do you mean that thickness is small? What we're assuming when we say this is that we can basically assume uniform stress along the thickness, that the thickness is small enough that the stress doesn't change. And if it does change, if you do have to consider that a change in stress along the thickness, then we would not be in thin-walled cylinder territory, we would be in thick-walled cylinder territory. And thick-walled cylinder territory mathematically, it's a little tougher, but it also has some very interesting applications. For you mechanical engineers, I have made the joke that mechanical engineers design weapons, but civil engineers design targets. Let's talk about weapon design, and let's talk about, let's say, the design of a barrel for munitions or bullets or what have you, okay? It is very common, everybody's thumbs up, goodness. It is very common that in that area, what you would do is, so you have the barrel, let's say the barrel of your gun, and you're wanting to install that in some sort of firearm. Okay, it is very common that what the manufacturer will do is they will take that cylinder and they will subject it to a heavy internal pressure. Okay, what they're doing is they're actually forcing some yielding inside the barrel. And you're thinking, wait, you want it to yield? Well, yes, in a controlled fashion. Okay? For example, if I fire a gun and the first bullet, all the stress from the bullet going through, the thermal load that the bullet applies, if that first bullet yields the barrel, then that gun is worthless after the first shot, right? What we want is for the barrel to be able to be used and reused and reused and reused over and over again, right? So the idea is that if here's my stress strain curve, right? Here's yielding, and then here's the nonlinear range. Maybe what I will do is I will take my cylinder and I will subject it to enough internal pressure so that I get some yielding through the pipe, so that instead of loading it and unloading it right here, maybe I'm unloading it and loading it right here. So now where the maximum stress was here, now it's here. So by forcing a little bit of that yielding inside, we're actually upping its capacity. Now you gotta be real careful with that because you don't want it to get too brittle, right? But the idea is that by exposing it to that internal pressure before it's utilized as a product, you're sort of prepping it for that repeated use. So that technique is called auto-frettage for you mechanical engineers in the room. So look at the civil engineer teaching you something about mechanical. Isn't that crazy? I know. Now, but ultimately though, unfortunately, we're talking about thin-walled pressure vessels, but the math is a little easier. But for you civil engineers whose eyes are glazing over hearing about the term thin-walled pressure vessels, and you're thinking, good Lord, when would a civil engineer ever care about anything like this? Well, there are some surprising analogies. In reinforced concrete design, when you are designing a circular column, right? So it's a circular concrete column and you're loading it like this. So inside the column, there's two types of reinforcement. There's longitudinal reinforcement, which runs up and down the length of the column. And then there's also spiral reinforcement. They have rebar that actually goes like this down the column. It almost kind of looks like a big spring from bottom to top. But that's inside the column. You can't see that after the concrete's been placed. But the way that we size that spiral reinforcement is we assume that the compressive load is acting on the column, and that internal pressure, the spiral reinforcement has to contain it as if it was acting like a thin wall pressure vessel. So there are some surprising analogies to this in various disciplines. And I mean, there's oodles of applications in biomedical where you have devices subjected to internal pressure. It could go on and on. Okay, let's actually get to some discussion, okay? So the way that we're going to do this is we're going to look at the resulting normal stresses that you would get from a thin wall pressure vessel. Now, what we're going to find is a very interesting result at the end. We're going to be able to relate the stress along this direction to the stress this direction with a very, very easy analogy. Now, what we're going to do for this is we're going to cut a section and we're going to look at this from an equilibrium standpoint. Okay? So I've cut a small component out of this, and there's some internal pressure inside the pipe, and I propose that developing some internal stress. So the idea is to try and figure out what is sigma 1 as a function of this internal pressure. And so let's look at the system parameters. Okay. So we have the applied internal pressure, we have the geometry of the cylinder. The radius or the diameter, doesn't really matter, you can use either one. The thickness of the cylinder, and then like how wide of a chunk we're cutting out of our vessel. Okay. Now, if we look at the pressure distribution and we're only considering half of it, well, I guess the question is just that. The pressure acts perpendicular to every point inside the pressure vessel, right? So if you look at the entire pressure vessel, all of these pressures self-equilibrate, right? They're you have the same amount going to the left as the same amount going to the right, etc. So what I'm doing is I'm isolating half of it, because if I look at the pressure distribution, let's look at this from a statics perspective. Let's look at this from a resultant perspective, okay? Every component of pressure, let's draw a component right here, is going to act something like that, like normal to the surface of the wall. A y component and an x component. But I propose for every arrow that I draw in one direction, there is a mirrored pressure distribution right here that has the same vertical component and the same horizontal component, right? Now, here's what's nifty, okay? I propose for any arbitrary component, the verticals cancel each other out, right? For any arbitrary component, there is a matching component in the other direction, and these two verticals cancel each other. But the horizontals sum up. See, I propose by only considering half of the shape, I can just look at it and tell you my resultant's horizontal. So this pressure is going to generate resultant force that way, and the vessel is going to respond with a force that way. Okay? So how do we determine all of this? Well, the pressure is generating a force. I propose simple, it's just pressure times area, and the area is the area of that box right there, which is 2 times B times the radius, or B times the diameter, or 2BR, whichever you want to call that. And so what is the pressure, what force is the pressure generating? It's just pressure times area. Take the pressure, multiply by the area, boom, that's the force that the internal component is applying to the cylinder. In this case, it's applying that sort of in the screen this way. So the cylinder must respond with the stress in the opposite direction. So set those two equal to one another, and boom, you get that stress. It's pretty easy. Pressure times the radius divided by the thickness. Very, very simple expression. So far, so good? All right. Now, that along the hoop. So I want to sort of focus right here. I want to look at this diagram. So what we were looking at is sigma 1. Sigma 1, so think about it from a directional perspective. Sigma 1 is along the direction of the circle, whereas sigma 2, 90 degrees off of that, is going to be in the longitudinal direction of the cylinder. Okay? So how are we going to determine that? Well, that one's actually a lot easier. Okay? All right, if I just cut a section like this, all right, so I say, all right, what do we got? We've got, well, the pressure inside is developing a force acting, we'll say, into the screen. And so that's just the pressure times the area pi r squared. And that has to be resisted by the cylinder, right? The cylinder's generating force in the opposite direction. And it's going to be the stress times the area. What's the area? Well, it's the thickness times the circumference of this circle. So set those two equal to one another, take a ratio, boom. And you get PR over 2T. But this is the crazy part. PR over 2T is your stress this way, but PR over T is your stress that way. So if you know the stress this way, the stress that way is just half of that. So that's actually a really easy formula to memorize, okay? So far, so good? All right, so we're going to look at a pipe that's carrying steam. Again, this is going to be a pretty short example. We're probably going to be done pretty quickly, but I want you to kind of understand what we're doing and why we're doing it. So we have a carrying steam at 500 psi. The pipe has an outside diameter of 16 inches and a wall thickness of 3/8 of an inch. And what we're going to do is determine the principal stresses, and we're going to determine the angle of orientation and look at the angle of orientation for maximum shear stress. Okay. All right. So why we're looking at maximum shear stress, but maybe I'll go ahead and do it now. So I'll do my best. Let's say you have a pressure vessel like this. Okay, this is the ground. Let's say you've got some stands on it. One of the ways to actually fabricate a pressure vessel is to take strips of metal, strips of sheet metal, and sort of wind it like this. Like if the easiest way to describe it is, have you ever looked at the cardboard for a toilet paper roll, or a paper towel roll? What you see is that what they've done is they've taken flat strips and they sort of coiled it like that. So you have, like, if you look at a paper towel roll, for example, here's the paper towel roll, and they have these like lines that go like that, right? You know what I'm talking about? Okay, so what they're doing is they're taking a strip of cardboard, of paper, and then twirling it, right? Well, what they do for pressure vessels is sometimes very similar. And so what you might see on a pressure vessel are welds that go like that. That makes sense? So if we're interested in normal stresses, we might also be interested in shear stresses, because those at a 45-degree angle, those are going to be our magnitude. So it's akin to what I showed you when the plate girder buckled. Okay. So let's write down some parameters so we know that P is 500 psi. Okay. Now we know that the thickness is 3/8 of an inch. Okay. Well, let's look at these data points that we were given. We were given an outside diameter of 16 inches and a wall thickness of 3/8 of an inch. Okay. Now, just so everybody is clear on the geometry, when we look at the pressure vessel, oh, I can do better than that. That's the best I can do. Okay, when we look at our resulting pressure vessel, okay, so here's the center. So obviously this dimension right here is the thickness, but when we utilize the radius in our expression is this value, okay? And specifically, the radius goes to the inside diameter, not the outside diameter. So what I'm getting at is we were given an outside diameter of 16 inches. Let's go back. If I have the outside diameter, how do I determine the inside diameter? Oh, minus 2 times the thickness. You got to cut a thickness out on either end, right? Now the radius, the inner radius could be the outer radius minus 1 thickness, so it doesn't really matter how you do it. But you got to account for the thickness on either end. So this is 16 inches minus 2 times 3/8 of an inch. So that's 3/4. 16 minus 3/4, 15, and 15 and a quarter. Therefore, the radius is the inner diameter over 2. So that's 7.5, 7.5 and a quarter, 1/8, 7.625. Did I do that right? We have our pressure, we have our radius, we have our thickness, so we can actually compute our stresses pretty easily. Sigma 1 is PR over T. Say it again. Second. Notice the units are really easy to deal with because we have a pressure, which is in PSI, multiplying it times R over T, inches over inches, so they cancel. Now, the beauty of this is that sigma 2 is just sigma 1 over 2. That is, I think I can do that one in my head. All right, let me stop for a second, see if anybody has any questions. So, if we're wanting to use Mohr's circle, okay, we don't have any our stress state according to our chosen coordinate system. So I'm going to say this is 0. Okay? Now, sigma x, sigma y, it doesn't really matter which one that you name which. Typically, I just call this sigma x. I call this 5083.33. Now, here's sort of the question. I haven't spoken at all about signs. Well, I guess I have indirectly. But are we going to take these as positive stresses or negative stresses? Let me go back. Positive normal stresses, are they tensile or compressive? Just in general. Like, have we been taking tension stresses as positive or compressive stresses as positive? Tension positive, because tension has a tendency to make an element longer, to increase its length. So we've been treating tensile stresses as positive, compressive stresses as negative. So I guess the question is, are these tensile stresses or compressive stresses? Well,
I think that's what he's saying, otherwise he could.
the balloon. Go to the balloon. I'm applying an internal pressure to a structure. What does the structure want to do? It wants to expand. It wants to get longer. These are both stresses. Now, before we move on, okay, I'll just put a little note here off to the side, right? Note, it's entirely possible that here's a pressure vessel, right? And we have our internal pressure, right? Which is generating a sigma 2, sigma 1. Right? That's what we're getting from these two expressions. But I could also take that pressure vessel and, oh goodness, hold on. I could also take that pressure vessel and just squish it. I could take that pressure vessel and twist it, okay? And let's say I squished it with some load P, or I twisted it with some torque T, etc. Each of those are going to generate their own stresses. So for example, sigma, so what does the P do, right? The P generates a sigma Y of P over 2, but that's going to be negative because it's in compression, right? And so I would just take whatever that value is and superimpose it with that, right? Now if I had a torque, the torque is going to generate a tau xy. This is of determining maximum shear. It doesn't matter whether it's positive or negative. We've already discovered that. But the idea is that you could take a pressure vessel and just add this stuff to it. So we got to compare P over 2. That's a mistake. Let's do P over area. Why don't I say P over 2? Yeah, P over area. Value, etc. But it's still just a circle with an outer diameter and an inner diameter, so you can compute an area and compute a J value just like we have before. But I just want you to recognize that we could take a pressure vessel problem and combine it with this stuff. Does that make sense? That T looks awfully like an I, so do that. Make sense? All right, so now plug this into Mohr's circle, but you're going to see an answer here in a bit that's a little silly, so, but just bear with me, okay? So sigma average, right? So the first thing we do is we compute the average, and the average is sigma x plus sigma y over 2. And so I can go ahead and tell you what the average of these two is. It's actually a nice, pretty whole number. It ends up being 76.25. The radius is, now we take that fraction minus that, so it's the same fraction as before, but we square it, and we add tau xy squared, which for our problem is 0, but I'm still going through the motions here. Let me extend that out a little bit. Can somebody tell me what we get for this? Here, I'll help you out. What are we going to get for that? Break out your Casio FX115 ES Plus or similar scientific calculator one more time. Got a second on that? Okay, all right, so here's the silly part, the quirky part to my problem. Oh. Sort of reinforce some concepts. So what is sigma 1 and sigma 2? Sigma 1 is sigma average plus R, and this is sigma average minus R. But can anybody tell me what these are going to be? They're going to be these, right? They're going to be 10,000. And so, first off, I think that should make sense if you consider our initial stress state. Let's go back to what a stress transformation is, right? Here's a stress state and another stress state, right? Take this stress state and rotate it even a little bit. I'm going to generate a shear stress, right? There's going to be a shear stress if I rotate it. But here's the thing. Both the unrotated state and the new rotated state, they also have to be in equilibrium. And so I propose that if I nudge it a little bit and generate a shear stress, the only way that that new stress state is in equilibrium is if I generate a shear stress, I got to drop a little bit of normal stress, right? Does that concept, does that idea make sense? Now, if that makes sense, then this has to make sense, right? Stresses are the ones where shear stress is 0. Make sense? Now, that doesn't mean that this calculation was worthless. Well, it was valuable for 2 reasons. One, it told me what the maximum shear stress is. And what is the maximum shear stress? And when you analyze, it's the radius. The other thing is that this analysis, this utilization of Mohr circle, becomes not just valuable but necessary when you have this vessel that also has a torque, a moment, an applied load, etc. Because you cannot get worst case shear stresses without Mohr circle. Because then you truly do have a stress state that's unique. So far so good? All right, now one final statement, and then we're going to call it. Let's compute sigma or theta p. Theta p is our worst case angle of orientation. And if I remember, the formula for this is what? Wouldn't it? Something like I believe it's something about like that. And let's plug and chug. 1/2 inverse tangent of what? What is the inverse tangent of 0? 0. Huh. So what does this tell us? This tells us maximum normal occur at an orientation of theta equals 0. But maximum shear stresses occur at an orientation of theta equals 45 degrees. And if you're wondering where I got the 45 degrees, well, the reason I got the 45 degrees is because all of our stress transformation expressions include a 2 theta, right? So that's like, well, okay, that's great, but that didn't answer. Okay, so where'd you get the 90? Well, I got the 90 from Mohr circle tells us that it's a circular plot. So if principal rotate 90, and I would get maximum shear. So in this case, it's theta equals 45. The reason I'm talking about this is because the problem asked, it said, okay, determine the angle of orientation for maximum shear stress. Well, for maximum normal stress, it's 0. For maximum shear stress, it's 45 degrees. Does that make sense? So that might be where I'm looking to see, are my welds behaving the way I want them to, etc. Let me stop for a second, see if anybody has any questions. Yes?
So would this still apply to like pressures, like?
Yeah. Oh, absolutely. Yeah. That would, if you had one that was fully loaded and fully pressurized, then it's like, okay, we need to determine the pipe necessary to properly contain that load. Because the idea is, okay, so in that land, it's like, what thickness does it need to be in order to safely resist the pressure? So let me talk about that real quick, and then I'll call it. So in fluids land, and I don't know if anybody's had thermo, or if you're in thermo now. I don't know if you might have started to see some of this a little bit in thermo. But the idea is, okay, we have to size the pipe in a certain fashion to maintain continuity, right? So the idea is, how big does the pipe need to be so that it has enough cross-sectional area to transmit the fluid, right? That's a fluids, Dr. SML or Dr. Wade question. And then the question is, okay, now the pipe is subjected to some pressure, what diameter or what thickness does it need to be so that the pipe doesn't crack? That's more of a question that we would answer here. All right. Lee, any questions? We're not quite done just yet.